All right, let's keep going. All right, I don't hear anything yet. We're safe to record this video. We're going to use GeoGebra to find these probabilities exactly. And the good news is you've done almost everything already that you need to do for this. So go to the probability part of GeoGebra. For binomials, we had to click to binomials, but normal is already right there waiting for us, which is great. All that you need to do, just like for normal, just like for binomial, we had to input n and p. Well, here we have to input what is our mean, what is our standard deviation. All right, and that's it. Okay, so let's solve some problems. Starting off, find the exact probabilities for example 1 using GeoGebra. So example 1, that was back here, right? This was, we never labeled it, but between 32 and 48, bigger than 48. So this is the probability between 32 and 48. This one was bigger than 48. The third one was less than or equal to 24, and then less than or equal to 54. All right, so these were the things that we did in the previous example using the empirical rule. Dum, 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 dum. I need to stop that. My cat is looking at me. She wants me to stop too. So let's calculate these with GeoGebra. So between 32 and 48, we have to put in the mean and standard deviation first. The mean, remember the problem said, was 40 inches of rain. The standard deviation, it said, we can double click, was 8 inches of rain. So now hopefully it scales by 5 instead of by 8. But hopefully if we compare this graph with the graph from the last video, it should look pretty similar. And we want to find out, when are we between 32 and 48? Well, this is just like the binomial distribution. We click right here. This right here is the one for between. And we want between 32, it's already there, and 48. It's this area. Does this area visually match what we had? This blue area, does it look kind of similar? It should. Yeah, the blue area looks similar to the GeoGebra area. Oh, okay, great. That's 68.27. What? Did you say it's 68.27, Jason? Or it's approximately equal to 68.27%. That's really close to the empirical rule. What a great rule. We estimated 68%. Well, if we use a calculator, it's 68.27%. Oh, what a great rule. Empirical rule. Good rule. 68, 95, 99.7% rule. What a great rule. Let's do the same thing for the other ones. Part B, bigger than or equal to 48. Well, we don't want the interval now. We want the greater than, the right-sided one, at least 48. Let's go down here, type in 48. Again, does this picture match our picture? The right-tailed blue starting at 48. Good, our pictures line up. We estimated, using the empirical rule, 16%. The exact is 15.87%. Oh, what a great approximation. 15.87%. Empirical rule is coming in clutch. Powerful, very powerful. Let's keep doing this. It would be a good idea to pause the video and do these last two on your own. Pause the video now, otherwise I'm going to give you a very judgmental look. And even if you don't pause the video, I'm going to give you a judgmental look because that's how videos work. But if you don't pause the video, this look is not for you. But if you didn't, no, if you, did pause the video, this is not for you. If you didn't pause the video, this is for you. All right. So hopefully you pause the video. And we want to do less than or equal to 24. So we go down to the bottom right, less than or equal to left-sided 24. And again, visually look. Yes, this is everything to the left of 24. This is what I want. 2.28% is what we have. That's pretty close to our estimation before of 2.5%. Do the same thing, less than or equal to 54. No, 56. No, it's 54. 96, 95, 99. And we didn't calculate that one with the empirical rule because it wasn't in terms of our standard deviation and mean. Let's do some more practice. Again, I think you can all do these. I have a lot of faith in you. I think you can do these without me, so feel free to pause it and do it on your own. We got a medical study in Wisconsin, and these found that a population of children were found to have serum cholesterol levels that were normally distributed with this mean. The cholesterol levels are apparently measured in milligrams per milliliter. So concentration, and a standard deviation of 0.3 milligrams per milliliter. Define and draw the normal model for children's cholesterol in Wisconsin. So draw, that's the easy part. Well, we're going to have to label it, but remember that all normal distributions look the same. You draw one, you seen them all. All right. So we'll have to label it. And then where are our tick marks? So the middle tick mark's easiest. That's just in the middle. And then kind of look back at it. The first tick mark is kind of at the inflection point right here, where the graph kind of changes from curving one way to curving another one. Inflection point, that's a good calculus word. And then the second one is when it gets really small. All right. So the first one's kind of at the inflection point. The second one is equally spaced away. And the third one. So again, we always start at the mean, 1.75. And then we keep adding standard deviations. 0.3. We add 0.3, we get 2.05. Add 0.3. Add 0.3. And hopefully, I wrote these correctly. And then just do it in the other direction as well. 1 standard deviation, 2 standard deviation, 3 standard deviations, and now we're subtracting 0.3. There we go. We have drawn the normal model here. And if we type this into GeoGebra, it should look pretty similar. And it also wants us to define. So drawing, that was what we did there. But we also have to define, and that is this. X is normally distributed with a certain mean and a certain standard deviation. The mean, 1.75, standard deviation 0.3, and X is the cholesterol concentration of a Wisconsin kid. Wait a minute. If you're a Californian, you're called Californian. If you're from California, Californian. Wisconsin, are you Wisconsinan? Wisconsinan? If there's any people from Wisconsin watching this, please let me know. Wisconsinite? Wisconsintonian? I don't know. So now we've finished it. We've defined, we've drawn it. We're good to go. Well, if a child has cholesterol levels of 2.11 milligrams per milliliters, what is the percentage of children in Wisconsin who have cholesterol levels that are higher than this child? So graphically, right, we're asking about what percentage of kids in Wisconsin have a cholesterol level higher than like 2.11. 2.11 is like maybe right here. And we're looking about what's the probability, what percentage of people are more than 2.11? Well, okay, well, just type that into GeoGebra. All right, this is part B. How many people are to the right of 2.11? Well, let's go over to GeoGebra, type in our mean, the average concentration, which was 1.75. And the standard deviation, I remember that one because I added and subtracted 0.3 a lot. And, before we even calculate this, let's look at our graph. Is this graph kind of labeled the same as ours? The middle should be at 1.75. The middle, yeah, sure, it's close to 1.75. And then is like the scale kind of right? Hard to tell. Hard to tell. Woo-wee. All right. What percentage are bigger than or equal to 2.11? So how do we write that down with math before we actually use GeoGebra? The probability that X is at least 2.11. There we go. Let's type that into Geog. Go over here. We want to see to the right tail, 2.11. Well, it says about 11.51%. Is the picture about the same as that red area? Looks about good to me. 11.51%. There we go. Find the percentage of children in Wisconsin who have a cholesterol level between those two numbers. Well, probability that we're between 1.30 and 2.23 is written like this. We can just type this into GeoGebra. I'm going to copy this graph down real quick. And apparently I'm writing it under part B, just like before. So we're expecting 1.3 is kind of like, 1.3 is kind of maybe right here. 2.23, that's pretty big. Maybe around here. We're expecting this area. Okay? This is what we're expecting. So let's type into GeoGebra and see if we got the same thing. This is part C. 1.3 to 2.23. Interval uses this one. 1.3 to 2.23. Does that look kind of like that red area? Oh, I went a little too far to the right here. Other than that, it looks pretty good. This is apparently 87.84. There we go. And that's using the power of computers. But we don't need 2 decimal places. 2 decimal points. We do want 2 decimal places. I did have a coworker when I was designing slot machines that when we asked him to give us an answer to 2 decimal places, he did do this. That's not what we mean. So I'm not going to name you, but if you were my coworker in Vegas and that was you, I'm publicly talking about you to my students. And this is our answer. Okay. Graphically, it's this area, it's this region. Numerically, we type it in and use our calculator, okay? What the calculator is doing, well, there's a long story for what that process is. But we're not going to be able to do these by hand. I cannot do this by hand. I'm pretty sure nobody can. I mean, you could get approximations by hand, which is what the calculator does. Anyway, good luck. Have fun. Also, update that's related to the end of my last video. I think they just came to check it out. There's no hammering.